In the last section, we talked about how to verify whether or not a vector was an eigenvector. But the real question you should be asking yourself is, well, how do we know? Like, how could we find them? What's a good way to go about finding these eigenvectors? And the answer is the characteristic polynomial. So the most important equation in almost all of linear algebra is this a minus lambda I. And the definition of the characteristic polynomial is the polynomial in lambda. So like, a polynomial is generally in terms of x, right? The independent variable here, though, is lambda. And if I calculate the determinant of a minus lambda I, then that's going to be my characteristic polynomial. And I'm going to set that equal to 0, and I am going to find the roots, and the roots will be the eigenvalues. All right, so I want to set this equal to 0. And you can see a quick example of that right below here in the 2 by 2 case. So notice what's really important, you'll get used to this, right? The a minus lambda I, all it does is it adds a minus lambda to the main diagonal entries, right? So I have a 5 minus lambda, right? The only non-zero entries in the matrix I, matrix IN, are along the main diagonal. So when I take lambda times the identity matrix, right, I'm taking the main diagonal entries and putting a minus lambda after every single one of them. Then when I calculate the determinant, you see I have the 5 minus lambda times 1 minus lambda minus 4. Sorry. Which means that I have this polynomial. That's my characteristic polynomial. I'm just going to mention one more property of the eigenvalues before I just start cranking through some examples. All right, so here's the key. In a triangular matrix, either upper or lower, the eigenvalues of A are the diagonal entries. Okay, so that actually makes a little bit of sense. If you think about how I'm calculating the determinant, I have this. If I expand down the first column, right, then I have A11 minus lambda times the determinant of this 2 by 2 matrix. Well, okay, so then I have, the AD minus BC. Well, there you go. C is 0. So I end up just having this polynomial where all the factors are just the eigenvalues, the 3 eigenvalues. So in a triangular matrix, the diagonal entries are the eigenvalues. So I have an example matrix here. You can see this B matrix, and I want to calculate its eigenvalues and the corresponding eigenvectors. Now, if you're going to use the characteristic polynomial, by the way, you can do this without this sims x, but to do this, you need the symbolic mathematics toolbox. All right, so if you downloaded this onto your hard drive, you can go back to the MATLAB install and go through all the same steps that you did for the UNG at the UNG-IT page to install. Except when you install, it'll come up and it has certain boxes X'd out. Whatever you had installed the first time, it doesn't include. And go ahead and click on the symbolic math toolbox and have it install, and it'll only take a couple of minutes because it doesn't reinstall the whole package. Just make sure that you reinstall the same version. So I'm running R2019B. So if I go back into R2019B and select install, then when the options to which packages to install comes up, I just select the symbolic mathematics toolbox. And that will make this stuff work a lot better. All right, so what am I going to do? Well, the char poly is the function we need. And what it normally does, and it'll do this without the symbolic math toolbox, right? It gives me the coefficient. So I know that I have 1 times x cubed, and the coefficient of the x squared term is minus 8, and the coefficient of the x term and the constant. All right, well, cool. All right, but what's really nice is if I can save this, because what if I have a 4 by 4 and I want to, do some polynomial long division to figure out all of its factors? Well, I can do this y equals char poly b, and then I put this x. That will, if the secondary input will tell it, hey, I want you to turn it into a, a symbolic cubic here. And the cool thing is that now I'm able to use a function called polynomial reduce. This is the polynomial long division. So I tell it, hey, I want to see if, let's just throw in x minus 1, right? That's always a good one to check. And it tells me the remainder. So when I do polynomial reduce, generally that's just going to be the remainder. All right, now that's not really what I want. So let me show you how this works. I can do, there are actually a couple of values I can get out of this function. So I'm going to go r comma q. So this is going to be the remainder and the quotient, right? So when I do this, and I know the remainder is not 0, but this is nice because now I know that the remainder is minus 3 and this is the quotient. So if I find something here that divides y evenly, I'll get a remainder of 0, and then I'll actually have a value that I know that is the reduced polynomial. Now, I'm not going to go through all of the theory about how to choose the best coefficients, the best factors to try dividing by when I'm trying to reduce a polynomial, but I will make it clear that we're looking at factors of 16. So the only things we can be looking for as factors are x plus or minus 1, x plus or minus 2, x plus or minus 4, x plus or minus 8. So when I go through to practice, right, I can check really quickly, see if a plus 1 fits. No, I get a remainder that's non-zero. Sorry, the remainder that's non-zero. So let me try x plus 2. Right, so this is how we do it. We do guess and check in your algebra course, where you can review this, an advanced algebra course. They sometimes use synthetic division to quickly check these. And let me try x equals minus 2, and there you go, boom. Now I have a quadratic, and I should be able to factor this one, right? That should be, looks like an x minus 2, so I'll have 2 of these, right? I'll end up with an x minus 2 squared because I have this one and the one I just found, and then x minus 4, right? So if I am setting this polynomial, right, equal to 0, right? It's not equal to 0, but I am setting it equal to 0. I set it equal to 0, solve for its roots, and then you'll notice the minus 2x plus minus 4x gives me the minus 6x, and then minus 2 times minus 4 gives me minus 8. Now, of course, anytime you do algebra and you're factoring, you want to double check it with expanding. So let me create another polynomial, right? So I'm going to have this be, right, x minus 2 quantity squared times x minus 4. So this is what we thought that the thing was, and I've got this option called expand, which does exactly what you think it would. Boom, it expands it out, and I can see, oh, well, in fact, I did get the right answer because here is the characteristic polynomial. Here is what I get when I expand this w, what I think that the factored polynomial looks like, and so now I'm clear. I know that I have an eigenvalue of lambda 2. Lambda equals 2, and that I also have an eigenvalue of lambda equals 4. And those are the only ones, right? The only eigenvalues I can find have to be from the characteristic polynomial. Now, this factor has a multiplicity of 2. So the lambda equals 2 eigenvalue also has a multiplicity of 2. And I'm not going to try to spell the whole word multiplicity, right? But it has multiplicity 2. So whatever the power is that goes with that eigenvalue in factored form, that's its multiplicity. And what's always true is that the number of eigenvalues, at least counted by their multiplicity, will sum up to be the same dimension as the matrix, right? So this matrix here is 3 by 3. So if I count by multiplicity, I'm expecting 3 eigenvalues. So I only found 2, but one of them had a multiplicity of 2, so I'm confident that I've found them all. So I just went back and simplified so we can see what's going on. So in the first step, I found the characteristic polynomial. I set it equal to 0 and factored it, and used the factored form to find the eigenvalue. So I just created an array lambda 2 comma 4. So now I know, just reminding myself what the eigenvalues are. So let's actually talk about how to find the eigenvectors. So you have to remember that we have this a minus lambda I, and I just want to show you, we're going to do this. I can do b minus, and I'm going to take the first eigenvalue of 2 times I3, right? I is EYE is the identity matrix of the 3 by 3 identity matrix, and there we go. That's what happens. So take a look, right? Compare. So what we're doing a minus lambda I, so there's a minus 2 after each diagonal entry, 8 minus 2, 10 minus 2, negative 10 minus 2. So the negative 10 minus 2 is 12, and the 8 minus 2 is 6, and the 10 minus 2 is 8. All right, so we're just going to create that matrix. I can also create the matrix for the eigenvalue of 4. And you'll see, again, all we're doing is subtracting 4 from each diagonal entry. So that's going to be negative 14, and that's going to be 4, and that's going to be 6. And that's what you see, negative 14, 4, and 6. Now, the eigenvalue, how do I find that? Excuse me, the eigenvector, how do I find that? Well, I'm finding the null space of this matrix, the A minus lambda I matrix. Okay, so what I'm going to do is I'm going to go back to the first. I'm going to start here. This is fine. And I want to row reduce it. But real quickly, let me just do one thing. I'm going to create this augmented matrix of B minus 4 times the identity matrix. So B minus 4I. But I'm going to augment that matrix with a vector of zeros. So I can use zeros, which creates a matrix, and I want a 3 by 1. And so then my little b, you'll see all I've done here is that I've added the column of zeros at the end. Okay, there's a couple of other ways I could have done that, but now little b is the matrix I want, and let me just hide it, and I want to row reduce it. There. Okay, and let me hide this one as well. All right, so now I have my row reduced form. Okay, well this is cool. What do I need to do? Well, first thing to notice is that x sub 3 is my is my free variable, right? So x sub 1 equals, and when I subtract it over, remember my equal sign is right here at that augmentation bar. And so when I subtract the 1.5 x sub 3 over there, I get a negative 1.5 x sub 3. And I know that x sub 2 equals minus, let's see, let's do 3 halves and 3 halves and 1 half x sub 3, right? And I know that x sub 3 is free. Okay, so hopefully you can see how to take that. We've practiced this vector form of our solutions. So I should end up with a vector that looks like what? I should have, let me get some spots in here. I'm going to have a 1. This is going to be a negative 3 halves. And this is going to be a negative 1 half. And that should be an eigenvector. Okay? How am I going to tell if it's an eigenvector? Well, I multiply, right? I take b times v, boom. And we notice that it is in fact a multiple, right? If I take 4 times 1.5, right, I get 6. So negative 1.5 times 4 is negative 6, right? I take a half times 4, that's 2. And it was negative, so it's still negative. And of course, 4 times 1 is 4. So what I found here is that b times, and let me call this v4, right? So I kind of have the idea that it's got a subscript that relates to the value of the eigenvalue, right? So I'm kind of thinking v4 as going with the eigenvalue of 4. And remember, I can double check this by doing b times v4 equals 4 times v4. Boom. And my logical array is all 1s. So I know that this is a true statement. So I know that 4 and v4 are a eigenvalue eigenvector pair. Now, I'll just say this, a lot of times we clear the denominators. This was a small point, but an important one, that there are infinitely many eigenvectors that go with any given eigenvalue. So what a lot of people would do is they would just come through here, they'd multiply this one by 2, they're just going to multiply through, multiply this one by 2, and then multiply this one by 2. And I'll just show you that even though I have a different looking eigenvector here for v sub 4, right? There's my v sub 4 vector. Even though I have a different look, this still holds true, right? So let me take off the logical operators there, and you can just see that, yeah, I now have -3 times 4, right? The eigenvalue, b times v is equal to the eigenvalue times the vector v. Okay, so we've got all of that, and I'm not going to save this very long. I'm going to ditch it because I'm going to come right back up here, and I'm going to go with a check on the eigenvalues for the eigenvectors for the eigenvalues of 3, and let me let me make the point here that now x sub 2 and x sub 3 are free. Why? Well, this is the multiplicity thing. So when I have a multiplicity of 2, I can end up with 2 different eigenvectors, one for each free variable. It doesn't always happen that way, but it can. And so let's see. So what I do is I set one of the free variables equal to 0. So I'm going to set this one equal to 0 and get an eigenvector for the other one. So this is, I'm going to create 2 vectors, v sub 2, 2 and v sub 2, 1, right? So the first vector v, and let me get rid of this crap so we can see what's going on. I'm just going to create them directly from here. All right, so v sub 2, 1, what's going on? Well, I'm going to set this one equal to 0, so I'm going to subtract this one over, and what does that leave me with? Well, it leaves me with that my x sub 1 should be equal to 1.5, while my x sub 2 is equal to 1, and my x sub 3 I set equal to 0. All right, and then v sub 2, what's going to happen here is that the middle value is going to be equal to 0, and I'm going to subtract this one over, so it'll be a -1. So, but they're going to have the same values, so it's going to be -1, 0, 1. All right. And now let me try multiplying v sub 2, 1. Boom. And you'll see that should be this times 2. Right, so 2 times 1.5 is 3, and 2 times 1 is 2. So this actually works. And by the way, we would probably, again, multiply through, right? So for v sub 2, 1, we're very much going to make this a 3 and this a 2 and this a 0. When I do the multiplication, now you can see that the 6, 4, 0 vector is definitely double the 3, 2, 0 vector. And then all we have to do is check the v sub 2, 2 variable, boom. And it's very clear that the -2, 0, 2 vector is double the -1, 0, 1 vector. All right, so that's how it works. I'm going to leave it there. Just to review, to get the eigenvalues, I find the characteristic polynomial and set it equal to 0. What's the characteristic polynomial? The determinant of a minus lambda I. This creates a polynomial in lambda, and I use the char poly function for that. All right, then after I have each eigenvalue, I create this matrix, a minus lambda I, right? And I augment it with the 0 vector like this. The 0 vector over here, I put zeros here, basically, right? So I augment it, and I'm finding a basis for the null space, right? So to connect this to earlier material, this is just finding a basis for the null space in vector form. And the null space is the eigenspace for this particular eigenvalue. So I find that null space in vector form. Any vector that I find in the null space, in the basis for the null space, will be an eigenvector for this matrix. So definitely do some practice on this, and I'll be back soon to talk about the coolest thing in all of linear algebra, a diagonalization. That's section 5.4.